Hello everyone, this is Yangyang Fu from Texas A&M University in the United States. I'm glad to be here today to talk to you about our recent research efforts on the containerized framework for building control performance comparison. This framework we developed mainly focused on comparing model predictive control, MPC, and deep reinforcement learning control in terms of a building energy system. This work is supported by U.S. Department of Energy. The agenda for today's talk will be, first I will introduce a little bit of background for this research needs, and then talk about the containerized framework for building control performance comparison. And follow that we can show some preliminary case study, and in the end I will provide some conclusions in our future work. For the background, so we know both MPC and the DRL has been widely investigated for building operations to achieve significant energy and energy cost savings in the literature. However, there are still lacks comprehensive comparisons of the pros and cons for both control strategies regarding building energy system control. To fill this gap, in this research, we proposed a scalable and a flexible simulation-based building energy and control system, and so that we can test different advanced control strategies like MPC and DRL. This framework can benefit the building energy community by providing scalable workflow to standardize the building control environments, and also provide guidance on how they can tune the DRL MPC controllers. The other benefits of this framework is that the control community also can use this framework to test their own control algorithm on standardized building control environments. In the end of this presentation, I'm going to show you some preliminary results to show you how we use this framework to compare the MPC and the DRL, and what is the preliminary conclusion of this comparison. So for this methodology, the containerized framework for building control performance comparison, you see in this red figure, this is the core part of this framework. The whole environment is containerized in a Docker file, Docker image. Docker is a virtual machine technique that hosts, for example, a Ubuntu operation system. And for this whole development, we rely on an open source programming language, Python. Inside this container, we have major three parts. One is the virtual building. The virtual building represents the high fidelity building models coming from like a Modernica Energy Plus or Spawn Energy Plus, and also provide some key performance index for the comparison. This virtual building models will be wrapped into a functional markup unit so that they can have a standardized simulation interface. And this FMU will then connect with the OpenGym interface through a newly developed FMU Gym interface library in Python. And through this standardized OpenGym interface, the virtual building will then talk to the advanced controllers, as shown in this right side. The controller part, we only provided two famous advanced controller. One is the optimal control, and the other is DRL control. For the optimal control, we provide major two parts. The reduced order models, for example, the state predictors, RC models for the zone temperature dynamics, for example, and also the output predictors. We also provide an optimizer, for example, Casadi, and some other open source optimizer like OpenNopt. For the DRL control, we integrate standardized DRL libraries, for example, the stable baseline, Tianshou, which is a very high performance Python implementation of different advanced DRL algorithms. And also we plan to provide some other DRL solutions because currently most of the DRL are very slow to provide sufficient control on the building energy system. We provided to reduce the training time by fitting extra models so that the DRL can speed up their training part, or by some other algorithm like transfer learning. And this whole framework can also be used by users at any operation systems. They can customize their own building control environments. And they can also customize the MPC DRL solutions that then connected with this framework. Three major functions for this framework. One is users can standardize their own building control environment by calling some of these key methods in the framework. And also they can implement the MPC for the standardized environment. They also can implement the DRL for the standardized environment inside of these containers. One preliminary case study for this framework is a sample fan coil unit system we considered for a single zone. The system will rely on a sample control logic to maintain the zone air temperature, which is to control the fan speed. The objective of this environment, we're trying to minimize the energy cost while maintaining comfort level. The rule-based control serves as a baseline control. The fan speed is controlled by a PI controller so that the zone temperature could be tracked at its set point. The MPC formulation for this sample environment is shown in this left side. The purpose is that we're trying to minimize the energy cost in this term, and also we're trying to minimize the thermal discomfort. The MPC relies on two models. One is the zone temperature dynamics model, represented as the ARX model, and also a power model in the format of polynomial equations. This model are identified using the training data, and we can get some kind of a model performance. For example, the zone air temperature prediction is within 3.2% errors, and the power prediction, the NRMC for the power predictor is within 10%. For the DRL formulation, we introduced this kind of state for this environment: time, zone air temperature, outdoor air temperature, solar radiation, and the power at current time, and three outdoor air temperature predictions in the next time step, and three solar radiation for the next three steps. The reward formulation of the DRL is exactly the same as the MPC, except that they have a negative sign. For this learning algorithm, we choose the double DQN with 4 layers of AN. And also for the training set, we choose the 500 epochs, and the control time step is 15 minutes, the same as the MPC. So some preliminary results for this comparison, we can see from this figure. The solid blue line is the RBC, and the dashed line is the MPC. MPC outperforms baseline in terms of the reward definition. The DRL algorithm learn a good rewards after a few of iterations, and it starts to be better than the baseline controller, and then start to approach the performance of MPC, and eventually will exceed the performance of MPC after a long training time. We compared the 3 controller performance after 500 epochs, especially for the DRL controller, and eventually we get this number. The MPC can save a significant energy cost, but the double DQN can help to reduce the thermal discomfort more than an MPC. So the conclusion is we provide a containerized testbed for standing this building control environment. We also provide a preliminary test on the single zone system, and we found that the both controllers require significant non-time to tune. And in the future, we're going to test this framework for more complex building system and provide more guidance on the tuning MPC and DRL. That's all from me today. Thank you.